happy to have Shachar Lovett giving this next talk about the sunflower conjecture. Shachar is an associate professor in the computer science department at UCSD, University of California, San Diego. He obtained his PhD at Weizmann Institute, did a postdoc at the Institute for Advanced Study, and has been a member of the UCSD ever since. He has worked on numerous areas and literally everything. And maybe the main common thread is this notion of structure versus randomness. Maybe I'll say something more personal. So I met Shachar, I think, in 2005 for the first time. Maybe he doesn't remember. He was interviewing me for a unit in the army. And I think it was like the hardest test ever in my life. And I think ever since, he's been giving me very challenging questions that were very, very intriguing and very, very good. So I'm thankful for him.
Yeah.
So let's hope that he will give another one today.
Perfect. Thanks, Avishai. Yeah, guys, I'm very happy to talk here, to be invited to talk here. And again, this is supposed to be like, it's and my goal in this talk is that everybody will understand everything. So please stop me and ask if you have any questions or comments or, tangential discussions. Everything is fine. Please, let's try to make this as interactive as possible. And also, there's going to be a natural place where I'll stop for a break before we get to slightly more technical material. And also, this is a sort of like a mesh of several talks I gave in the past. Some on the sunflower conjecture, some on random restrictions are going to come up. So if some of you have seen some of the things, and then feel free to leave or not, or whatever you want. But it's hopefully there'll be something new here for everybody also. Okay, and also I want to add that this is all joint work with three people, with Ryan Alweiss, who's a grad student at Princeton, Kewen, who at the time was an undergrad at Peking University, is now starting PhD student at Berkeley, working with Avishai, and with Jiapeng Zhang, who just started, who was my previous PhD student and is now starting a faculty position at USC. Yeah. Okay, good. So here is the main theme of this talk. So I'm going to talk about this conjecture called the sunflower conjecture in combinatorics, and in particular, how it's connected to questions and topics that come up in theory CS. And there are two themes I want to emphasize in this talk because I think they are broader than just this specific work, and I think people could utilize them in other areas as well. One is this connection that we've been having for many decades now between TCS, theoretical computer science and mathematics, and the other one, like Avishai was saying, this notion of structure versus randomness, which is a very useful paradigm for many problems, including the one I'll talk about today. So we have this sort of mathematics and TCS, theoretical computer science, and there's this sort of nice bridge between them. And one direction is maybe the more obvious one, where we use math a lot in TCS. We want to solve problems that arise when you're thinking about computation, and you need a lot of mathematical tools to solve them, coming from various areas. But I think what is even more interesting sometimes is going in the reverse direction, where you can use a lot of computational thinking to study problems in mathematics that on the surface don't seem to have anything to do with computation at all. They're completely pure math questions, but somehow having the type of computational thinking seems to be really useful. And here I listed some examples. There are many other examples, and sometimes I just want people to sort of, even if you're studying like pure math questions in combinatorics or in other areas, sometimes it is useful to at least be aware to this type of computational thinking that comes up in TCS. And again, this talk will be one such example. Okay. The other general paradigm is this notion of structure versus randomness, where you study some type of mathematical object, maybe it's a graph or a function or a set system or whatever you're studying. And there are usually two types of structure versus randomness that come up. The first type is what I would call a dichotomy, where you could show that every object is either structured or pseudo-random. And again, for now, think of both of them in the conceptual level. So structure means having some type of structure while pseudo-random means looking like a random object in a certain way. So that's one type, and the other type is maybe a more refined one, but maybe more widely applied, is more of a decomposition type, where you say, well, my object is not purely structured or purely pseudo-random, but I can decompose it into two parts, one part being structured and the other part being pseudo-random. That's more common. And again, what do we actually mean by structured pseudo-random? Really depends on the application. So usually one of them would be natural, and the other one would just be the complement. So maybe, you say, well, maybe there's a very natural structure that if I have it in my problem, I could make progress on it, and lacking this structure, I will call it pseudo-random, or maybe it's the other way around. Maybe there's this very natural, random-looking phenomena that I can understand, and if I don't have it, I would call this structure. So whichever one you're choosing, naturally, the other one would complement it, and then you're trying to understand how they look. And again, there are many examples in the literature. So here again, I listed some. So maybe the most famous one here is the semi-ready regularity lemma that he used to prove his theorem, and which says that any graph can be decomposed into basically a small structural part, and the remainder being pseudo-random. So this would be more of the decomposition type. And again, this has been influential in so many works in combinatorics, graph theory, and also in CS and other areas. And there are many other examples like that. Okay, so this is this general notion of structure versus randomness. Now let's start talking about the topic of this talk, which is sunflowers. So here's a sunflower, but we will be actually interested in this type of sunflower, which looks similar, but not quite the same. This is like the sunflower in combinatorics. So what is a sunflower? So it's an R sunflower. R is a parameter. It's a collection of R sets, S1, S2 up to SR, with a very specific intersection pattern. So all the pairwise intersections must be the same. So here you see in this diagram, so I have 3 sets, and the intersection pattern, the Venn diagram is very specific. So all elements either belong to all of the sets, or maybe just to one of the sets, or maybe to none, but then I don't care about them. So, but like, for example, what I don't have are elements belonging to 2 sets, but not to the 3rd set. So this is a sunflower. This is a sunflower with 3 petals, 3 sets. In general, you can have 4, 5, 6, or some number. So 2 doesn't make any sense. Every 2 sets correspond to 2 sunflowers. So the first interesting case is 3. So 3 petals. And again, what these common elements that belong to all of them, we call the kernel. And these sets we call the petals. So it looks like a sunflower. Or it's like a flower. So this is a sunflower. And the basic question that we are going to study is this Ramsey type question that says, if you're given a set system, so a set system is just a collection of sets, a family of sets, maybe with some restrictions on them. How large should the set system be so that it must contain a sunflower? So can I always say that if I have a large enough set system, then it necessarily contains a sunflower with some given number, like 3, 4, 5 petals? Okay, so why is this an interesting question? Well, usually it's interesting because if I give you arbitrary sets with arbitrary intersection patterns, it's hard to argue about them. But sunflowers have this very nice, simple intersection pattern, which in many applications make them much easier to argue about. And in fact, sunflowers, I'll tell you a bit, they're introduced in the 60s, and there are probably, dozens of applications, if not even more, both in math and in computer science. And again, you need to, so now there are 2 variants of this question that you can think about. One is the original one introduced by Erdos and Rado in 1960, where we bound the size of the set. So we have a family of sets, and each set has size at most some parameter. We're going to call W. That's one variant. The other variant, introduced by Erdos and semi-ready about 20 years later, is where we don't bound the size of the sets, but instead we bound the size of the universe. So we have sets out of n elements, but the sets will have any size that you want. And both types are interesting, and both have many applications. And I'll talk about both, but mostly I will talk about the Erdos and Rado variant. This is like the more general one. The Erdos semi-ready one is actually a special case of the Erdos and Rado one. So what we want to prove that every large, well, not field, but a set system, I guess, contains a sunflower. Here in this picture, you see that it's very large field, and in fact, it must have a sunflower inside it. And so again, talking about this Erdos and Rado setup. So I will assume to have a set system, F, this curly F, and I will assume that all the sets in it have size exactly W. Now you could also assume the size at most W, it's basically the same thing, doesn't change anything. But just for simplicity, I will assume here in this talk that all the sets have size exactly W. And I'm going to think of R, which is the size of the sunflower, how many sets I want to find in the sunflower, some fixed constant. And mostly I'm going to think about 3 in this talk. So 3 is a good number to keep in mind. So I want a sunflower with 3 petals, 3 sets. And the question is, how many sets do I have in my set system so that it must contain a sunflower? Is there even a bound? Could it be that I can find infinite set systems where all the sets of size W, but still contain no sunflower? And the sunflower lemma that Erdos and Rado proved about 60 years ago said that, well, no, there is a bound. And the bound that they proved is this. So if I want to find an R sunflower, and I know all the sets of size W, or at most W, then if you have more than W factorial times R minus 1 to the W, then your set system must contain a sunflower. Now a bit about the asymptotics here. Well, if R is 3, then this is like 2 to the W, this factor. By the way, when I move my mouse, can you see it? Just verify that. Avishai or Prasad?
Yes.
Verify? Yes, good. Okay. And here, this is a more dominant term. This is W factorial. So this behaves like W to the W. So the question is, well, what's the right answer? And it turns out there are examples you can build, and I'll show you an example in the next slide, where you can get this to be true without this W factorial. So there are examples of size exponential in W with no sunflower. But the lemma that they prove says, well, you need slightly more. You need W to the W. So really the whole question is, do you need this W factorial factor or not? So Erdos and Rado conjecture that you don't need it. They said, well, for every R, let's say R is 3, there is some constant such that if your set system is more than this constant to the W, so just singly exponential in W, then it must contain a sunflower. And we know it has to be exponential W, but the proof is slightly worse, W to the W. And the question is, which one is the right answer? See that the question in the chat. We encourage you. Okay. Yes. Perfect. Yeah, turn the video on. It will be nice. Then we get to see all of you. Perfect. Okay, so now the whole question is, which one is the right answer? So now let me show you an example. How do we construct sunflower-free families? So let's, for concreteness, think about 3. So I want a set system that does not have a 3 sunflowers. So here's one way to do it. So my universe is going to have 2 times W elements, or 2 W elements, but I'm going to arrange them in a grid where the height is 2 and the width is W. And I'm going to take all the sets of the following form. In every column, choose one of the 2 elements. Okay? So I claim that, first of all, I have 2 to the W sets here, but they do not have a 3 sunflower. Why? Because in every column, if I have a 3 sunflower, then either all elements have to be distinct or the same. Well, they can't all be distinct, or they must be the same. So in fact, they must be the same in all columns, so it must be the same set repeated 3 times. So if this wasn't clear, you just verify to yourself that this specific example does not have a 3 sunflower. So there is a set system of such 2 to the W, which is not 3 sunflower. And the conjecture is that maybe replacing these 2 with a large constant, like 100, maybe every family of 100 W sets does not contain a 3 sunflower, but we do not know. That's a conjecture. It's a sunflower conjecture. Okay. Now I have one slide about this Erdos summary settings because I think it's interesting for some applications. So here we're thinking about a set system where we don't bound the size of the sets, but instead we're saying that there are only n elements. And turns out this is actually a special case of the Erdos and Rado sunflower, both lemma and conjecture. So the sunflower lemma implies the following results. If my set system is really close to maxima, so 2 to the n is all the sets I could have. So it's 2 to the n, but I'm saving some constant root n in the exponent. Then it must contain an R sunflower. And this constant depends on R. So you can prove that just by a simple reduction from the Erdos and Rado sunflower lemma. And similarly, by a reduction from the conjecture, sunflower conjecture, It said that actually, even if you can save much more, you can save something linear in n and not linear in root n, and still you must contain a sunflower. And the nice thing about this Erdos summary setting is, in fact, we know this is true only for r equal to 3. So Eric Naslund proved about 2 or 3 years ago that the Erdos summary, the sunflower conjecture, is true for r equal to 3. And the proof is algebraic. Now, I'm assuming many of you have heard about this resolution of the cap set problem several years ago. And what Naslund used is a variant of the same proof technique to prove this result as well. But the proof doesn't seem so far to generalize for R being 4, 5, or any number more than 3. So far we only know that this conjecture is true for 3, but not for 4. So there's a very tantalizing question. Can this algebraic proof technique be generalized to other problems? But this is not going to be the topic of this talk. The proof I'm going to present today will not be algebraic. It will be more of like a softer proof that will be easier to modify. So usually one, algebraic proof, like there's one general meta comment, I would say, algebraic proofs are like magic, right? When they work amazingly well. They give you very nice, succinct proofs for whatever you're trying to prove. But when they don't work, they fail completely. And it's very hard to modify algebraic proofs to get them to work in other variants. While when you have softer techniques, sometimes the proofs are messier. Maybe you don't get tight bound sometimes, but they're usually easier to modify and get them to work in other settings. And the proof I'll show you today will not be algebraic.
Shachar?
Yes.
Can you mention, so the sunflower lemma implies these parameters. What is known with the current knowledge? This is a sunflower lemma. So the sunflower conjecture, what does it imply?
So the sunflower conjecture implies a bound I have here that the optimal bound is the exponent is n minus cn.
Okay, I see.
And the result I'll tell you about in a bit will prove n minus c times n over log n.
Okay, good. Thank you.
What you save is n over log n.
I see.
So you prove the saving from root n to n over log n. Yes, good, perfect. Any more questions? Yeah, okay. More people should ask questions, not just Avishai. It's good that Avishai is asking questions.
It's very clear so far. So
good, perfect. So what's the result I want to tell you about? So we have this again. From now on, we're just going to switch this Erdos and Rado setup, all the set of size W. And to be concrete in this talk, I'll focus on finding the 3 sunflower. And you'll see that 3 is nothing. There's nothing magical about 3. It generalizes to 4 and 5 and 6 and so on. And so here's what we know. So the sunflower lemma I told you about gives this bound of W factorial times 2 to the W, which is asymptotically something like W to the power W. And there were 2 improvements since the 60s. So Kostochka, about 20 years ago, improved the exponent by some low order terms. And then about 2 years ago, Fukuyama had a proof that improved the exponent by some constant. And the new bound I'll tell you about improves the base to something like log W. So now what we know is that this is true if the set system exercises something like log W to the W instead of W to the W. So we're getting closer to the conjectural bound, but not quite there yet. And if you sort of want to talk about the results in slightly more detail, so what we proved, this was in this work with Ryan Alweiss and Kewen and Jiapeng Zhang, was the following bound, where we had this R log W to W bound that we were trying to get, and you'll see later why this is like a natural barrier for our techniques. But somehow we had to suffer this annoying lower order term here that somehow we couldn't get rid of. And then there was this follow-up work by Frankston, Khan, Narayanan, and Park that they actually were able to remove this lower order term. And they got this bound that is of the best we know so far, which is some constant R log W to the W. And the reason they really cared about this was not because of the sunflower conjecture, but because what they realized is the same proof techniques actually proves another conjecture, which was called the threshold expectation conjecture of Talleyrand. I'll tell you a bit about this later on in this talk when you see some of the techniques that come up. But I'll say one word about this now. It's basically this conjecture, once you prove it, allow you to reduce many of the questions in random graph theory to basically simple calculations. So if you want to ask questions like, if I have a random graph, what is the edge, what is the threshold for finding a matching or a Hamiltonian cycle or whatever thing you're interested in? So before, people had like very complicated ad hoc proofs. And now once this conjecture is proven, it just reduces of simple calculations for different problems. So I think this was very nice. I didn't know about this conjecture. It was very nice to learn about this. It was even nicer to realize that our techniques, once we improve them, actually prove this conjecture. And then there'll be sort of two new proofs of the same bound. So Anup Rao proved last year. He was able to simplify the proof using information theory. And then recently, about 2 or 3 weeks ago, so Terry Tao gave an alternative proof for, again, given the same bounds, also using information theory in slightly different ways. So now we have like maybe 4 proofs for the same result. And I think it's useful because once you have different proofs, it maybe makes it easier to think, well, how could I maybe get better bounds, right? So this is very useful, having different proofs for the same result. Okay, but the one I'll tell you about today is mostly this one, and I think it's conceptually it's easier to understand. So now let's talk about the proof. So again, just remember what we're trying to prove here. So we're trying to show that every large enough set system where all the sets of size W must contain a 3 sunflower. And I'm going to use the following notation: a W set system. So a W set is a set of size W with W elements. A W set system is a set system, a family of sets, where all the sets have size W. And what we're going to prove is the following slightly weaker bound, where every W set of size log W to the order W contains a 3 sunflower. So so what you really wanted was to improve this O to 1, but we won't get this. There's like 2 or 3 here. But the proof will be slightly easier. That's what I want to prove to you. And again, the high-level approach we're going to take is the following. We're going to use 2 main ideas: structure versus randomness, and this bridge between TCF and math. And in particular, as we'll see later on in this talk, there's going to be a very natural connection between set systems that we study in combinatorics and these objects called DNFs, Disjunctive Normal Forms, that are widely studied in TCS. And I'll explain what they are when they come up. But this connection was very, very useful for us for deriving this result. So first of all, structure versus randomness. So now is actually a very good time to actually tell you the proof of the sunflower lemma that Erdos and Rado proved 60 years ago. And the proof, as you see, is very, very simple. It actually was going to completely fit in this one slide. So here's the bound that we want to prove. I have a set system that has a set of size W. Its size is more than W factorial 2 to the W. It must contain a 3 sunflower. So the proof is by induction on W. And the first step is this simple observation that if my set system contains 3 disjoint sets, I'm done. Why? Because 3 disjoint sets correspond to a sunflower with an empty kernel. Like in the sunflower, we are not requiring the kernel to be non-empty. Remember, the kernel are all the elements that are common to all the 3 sets. Well, if all the 3 sets are disjoint, then they are a trivial sunflower. So we are done. So otherwise, I'm claiming that there are 2 sets in F whose union must intersect all other sets in the family. Why? Take one set. Now, if all the sets intersect it, we're done. Otherwise, there is a second set disjoint for me. Take it. Now I have 2 sets. Now, by assumption, there is no third set disjoint for both these 2. So every other set must intersect one of these 2 sets. So the union intersects all sets in the set system. So what did I find? I find the union of 2 sets, well, had at most 2 W elements. So one of these 2 elements must belong to many, many sets. So I have 2 W elements that hit all sets in the set system, right? Every set in my set system contains at least one of these 2 W elements. So let's take the element that belongs to the largest number of sets in the set system. So just by basically union bound or pigeonhole or whatever, there is an element that belongs to at least 1 over 2W fraction of sets in the set system. So let's take this element and take all these sets. Now I reduced my set system by factor 2W, but the benefit is now all the sets in my set system contain this one element. So I can remove it. Now all the sets have size W minus 1, and I can use induction. Right, I receive to these sets, and then use induction for W minus 1. And you see the bound that you get is 2W times 2W minus 1 times 2W minus 2, and so on. So you get exactly this bound, W factorial times 2 to the W. So we're done. That's a proof. We're done. So the proof is very, very simple. And the question is, well, how can we hope to do better? So actually, to see that, I want to introduce one notion and then show this proof again using this new language that's going to maybe hint how we can hopefully do better. So what I need is this one definition called a link. So I have a set system F and I have a set T that is some arbitrary set, not necessarily in the set system. And we need this very, very important definition of a link. So the link of the set system F at the set T is the following set system. So I take all the sets in my set system that contain T as a subset. And just for subset means subset or equal always. So subset or equal. And I take all the sets and then I remove T from them. So just to make sure that we all understand this, I have a couple of examples here. So if my set system is this set system that has 5 sets, and I look at the link of the set 1, so I take all the sets that contain 1, so it's 1, 2, and 1, 3, 5, and I remove 1 from both of them. So I get the sets 2 and 3, 5. And if I look at the link of the set 2, 3, then I take all the sets contain both 2 and 3, so I have 2, 3, 4, and 2, 3, 6, and I remove 2 and 3 from both of them, that's 4 and 6. So this is a link. And now what we need is the following observation. It's very simple, but very, very powerful. If a link contains a 3 sunflower, then the original set system must also contain a 3 sunflower. Why? Because if a link ft contains a 3 sunflower, then here the 3 sunflower, S1 minus t, S2 minus t, S3 minus t. So if I just add t to all of them, I just add t to the kernel, the original sets S1, S2, S3 are also a sunflower. So it's actually, it shows that if for some reason it's going to be easier to find a sunflower inside the link, then we can reduce to a link and find a 3 sunflower there. Okay. So now, given this definition, this observation, let's go back to this proof of the sunflower lemma. So I'm going to prove the same sunflower lemma again using this link terminology. So again, the proof is by induction on W. And now I'm going to do it in the other direction. I'm going to say, well, assume there's an element X such that the link of X, the single element, is pretty big, has size more than f over 2W. In this case, I'll restrict to this link and use an induction for W minus 1. So if there is a large link of a single element, then we use induction. Otherwise, what we're going to prove to you is that there is no large link of a single element, then your set system must contain 3 disjoint sets. So we're done. That's like a trivial sunflower. And the proof is exactly the same as before, but just for completeness, I wrote this here. So let's go through it quickly. So take any set in the set system, any element in it by assumption, the link is small, it contains fewer than f over 2W sets. So totally, how many sets does S1 intersect? It has W elements. Each one intersects that many sets, so just union bound, it intersects less than half the sets in the set system. In particular, there must be another set in the set system disjoint from S1, take it. By the same argument, S2 also intersects less than half the set in the set system. So overall, there must be a set S3 disjoint from both S1 and S2, and we're done. Okay? So it's basically the same proof as before, just in the contrapositive form. Right? But now that we're seeing the proof in this language, it sort of hints how can we hope to improve this. So what can we hope to do? Well, why just look on links of a single element? It seems very restrictive. Why not look on links of more than one element? That's what we're going to do. So assume that our goal is going to be to prove the following result. If f is a W set system, what we want to prove is for some parameter k that we try to optimize, if f has more than k to the W sets, it must contain a 3 sunflower. And what we're going to, well, the sunflower lemma, as we said, use links of size 1 and use induction for W minus 1, but we're going to use larger links. So what we're going to say that, well, what is a structured case? There is some link that is big. So assume there is a set T such that the link of the set T, meaning all the sets in the set system containing T as a subset, have many of them. What is many? More than whatever this parameter k we're trying to get to the power W minus T. when I'm claiming in this case, we can just use induction, right? It's the same statement. So we can just use induction here. So the pseudo-random case would be, what if no link is big? So the sunflower lemma used the assumption that no link of size 1 is too big. But now we're going to have this stronger assumption that no link is too big. Yes, sorry, go ahead.
Yeah, so you have K as K of W. So you got to be a little bit careful that K doesn't, as a function of W isn't too bizarre for this to
Yeah,
work.
so for example, you want K to be increasing with W. So K, you want to say increase W, K cannot decrease. That's all things that you really need here. K is like a weekly increase in W.
Sure.
Thanks. Oh, I think there's a question in the Q&A now. So it's going to answer live here. Both proofs of the sunflower lemma generalize naturally to R more than 3. Yes, everything generalized to R more than 3 in a very natural way. And I'm just using R equal to 3 here because it's just easier to explain. But everything, there's going to be exactly one point where 3 is going to come up, and I'll show you what this is. So yeah, so far everything generalizes. Okay. So now let's define more specifically what this pseudo-random case here, where basically no link is too big. So we have the following definition. A set system is K-spread if the following condition holds. For all links, all sets T, if I look on the size of the link, Ft, it is much smaller than the size of F. And by how much? By a factor of K to the T. So there is this exponential decay in the link size, where the larger I choose T, the smaller the link gets. Okay? And crucially, we'll need this assumption for all sets T. So the sunflower lemma proof uses just sets T of size 1, but we will use all T's. Okay, so again, the larger I choose K, the more pseudo-random it is, they shrink faster. So the sunflower lemma show that if K is more than 2W, then F contains 3 disjoint sets. And in fact, they only needed T of size 1 here. But what we're going to prove that if we use all T's, we can improve the bond from linear in W to logarithmic in W. So that's going to be the main technical part. We're going to prove that if we contain if K is more than log W, roughly, and for all sets T, the links shrink with the base of the exponent being K, then your set system must contain 3 disjoint sets. Okay. So now is going to be a good point to talk about how we're going to hope to prove that. And here we're going to connect set systems and DNFs. So I have one slide introducing DNFs. If some people here in the audience maybe coming more from like a pure math background, maybe haven't seen them or forgot what they are. Although I do think we teach them in discrete math. So a DNF is an OR of end of literals. So a literal is a variable or its negation. A term is an end of literal. So here's an end, and here's an end, and here's an end. This is a term. And when we OR them, we call this a DNF. And there's going to be one parameter that's important here in this talk, which is called the width of a DNF. Width of a DNF is the maximal number of variables appearing in a term. Like in this example, it's 3. So the width of this DNF is 3. And we will need some restriction of a DNF that would naturally correspond to set system, which is a monotone DNF. So a monotone DNF just means there are no negated variables. So this should be no negated variables, not terms. So meaning I only have positive variables like x1 and x3. It's like I don't allow negation variables. Okay, this is a monotone DNF. And I'm claiming that a monotone DNF naturally corresponds to a set system. And maybe the easiest way to see it is by this example. So here's a set system, 3 sets. And basically, I translate every set into the corresponding end of variables. So the set 1 to 3 would correspond to x1 and x2 and x3. And the set 3, 4, 5 would correspond to the term x3 and x4 and x5 and so on. So it is this very nice correspondence. But I mean, so far it seems like sort of abstract nonsense. It's just like 2 different ways of writing lists of numbers. So I want to claim that there is actually a deeper connection between set systems and DNF, not just 2 different ways of writing lists of numbers. And this will come from the following observation, that when you think about DNFs, there are natural questions that come up if you think, well, what do we typically try to analyze about DNFs coming from the CS perspective? And one very natural thing is asking, well, given a DNF, how many satisfied assignments does it have? If I set x1, x2, x3, and so on to true or false, how many choices do I have making this DNF true? Or an equivalent way, if I choose these variables randomly, true or false, what's the probability that it's going to be true? And we would actually need this for something that's called the p-bias distribution, where we're choosing x in 0. And think of 0 as false and 1 as true. So false or true, 0, 1 to the n. I'm saying it's not 50-50, but there is some bias towards some direction. So I'm going to use p-bias to say the probability xi is 1 is p. And p will typically be something much less than a half. So I'm going to choose my every xi to be true with some small probability p. And I'm asking, let's try to analyze the probability that this DNF, this monotone DNF, is satisfied. Okay, well, this will somehow be important for us. And I'm saying the fact that this is a natural question to ask about DNFs would suggest that it might also be a natural question to ask about set systems. So I'll one definition here. So I'm using curly f, capital F for a set system, and small f for this corresponding monotone DNF. And I'm going to say this DNF is PQ satisfying, so P and Q are two numbers between 0 and 1. If the following thing is true, I'm choosing my inputs coming from this p-bias distribution. I mean, every xi is 1 probability p independently. And the probability DNF is 1 is pretty big. It's more than 1 minus q. Okay, so the smaller p is, it's harder to satisfy the DNF. And the smaller q is, I'm requiring more from this DNF. So a smaller p and smaller q is a stronger condition. And now let's see what this translates to when I'm going back from this monotone DNF setting to this set system setting. So first of all, what is this p-bias distribution? Well, it's just a p-bias distribution over sets, right? So I'm choosing a subset of my universe. Let's say if a universe is n, so I'm choosing a random set in my universe where every element is included with probability p independently. That's a p-bias distribution. What does it mean that the set system is PQ satisfying? Well, it's the following condition. So I want some term in my DNF to be satisfied. A term is satisfied if all the elements in it are 1. So I'm asking, what's the probability that there exists a set in my set system that is completely contained in W, right? W are all the elements that were set to 1. And the DNF is satisfied if there exists a term where all the elements are set to 1. So equivalently, there is a set in the set system completely contained this W. Okay. So I'm claiming that now this question, which might not be a natural question to ask if you're studying set systems, becomes natural once we view them in this alternative way as monotone DNFs. So the question we're going to ask about set systems is the following question. Choose a random set W from some p-bias distribution. What's the probability that they completely cover some set in my set system? And now here's a very natural question. What does this have to do with sunflowers? This seems completely, out of nowhere. How can I hope to anything like that to study sunflowers? So I want to show you that there's actually a very deep connection between these questions and sunflowers. So I want to prove to you the following lemma, and this will sort of connect these things together. So again, I copied the definition at the top, and I'm going to set P and Q to be a third. So I'm going to say if F is 1/3, 1/3 satisfying, then it must contain 3 disjoint sets. What is 1/3, 1/3 satisfying? So I'm choosing W from this U 1/3. So every element is included probability 1/3 independently. And now I want the probability more than 2/3. I'm going to contain a set in my set system. And I'm claiming if this happens, this type of probabilistic statement, then your set system must contain 3 disjoint sets. And the proof is simple. It's going to fit in the bottom of this slide. I'll show you this in a second. But I just want to make one comment here that this is one way of connecting, I would say, sort of soft techniques about, some probabilistic statements where we have parameters like P and Q we could adjust, to a very combinatorial question of property about a set system containing 3 disjoint sets. So this is why sometimes it is useful to try to use more softer techniques. You can adjust parameters because they give greater flexibility. Like for example, this was one question somebody asked before. If I wanted to change this 3 to a 4, if I want to have 4 disjoint sets, I would just change those two parameters to 1/4, 1/4, and everything would generalize. Okay, now let's see the proof. So I'm going to consider the following experiment. I'm going to take all the elements in the universe, and I'm going to randomly color each element with one of 3 colors, either red or green or blue. Okay, that's my experiment. And I'm going to look at the marginal distribution. So I'm claiming that the red marginal distribution is exactly U1/3, right? But every element is colored red with probability 1/3. And the same is true for green and blue. So of course, they are not RG and B are not independent, but the marginal distribution of RG and B, each one is U1/3. And now let's ask, what's the probability that my set system contains a set where all the elements in the set were colored red? So I call this a red set. Well, it's exactly the same as asking, what's the probability that there exists a set in my set system that is contained, entirely contained, inside the set of red elements. Now, because R has a marginal U1/3, and because I assume this is 1/3, 1/3 satisfying, this probability is more than 1 minus Q, more than 2/3, right? Just by definition. And similarly for green and blue, right? But both green and blue have marginal U1/3. So what do we get? Probably more than 2/3, I contain a red set, a green set, and a blue set. So by union bound, with positive probability, my set system contains a red set, a green set, and a blue set. So in particular, the 3 sets must be disjoint because, well, obviously, right? Like all the elements of the first were colored red, and the second were green, and the third was blue. They can't have common elements. So that's it. That's a proof. So actually now is a good time for people to maybe stare on this slide for like, 10, 20 seconds and see if you have any questions. Because, I mean, although technically it's simple, conceptually it shows that we can reduce from these questions, this combinatorial question about finding 3 disjoint sets, to this sort of probabilistic statement of showing that the set system is satisfying. So maybe I'll give people some time to digest this and see if they have any questions.
One thing about going back to the comment on soft techniques and this proof, typically soft techniques, they tell you that a large number of some combinatorial structures exist. So does your proof also tell you a whole number of sunflowers exist?
Yeah, yes, but for this you don't need this. You just sit in a black box. Because you find a sunflower, you remove it, and you keep doing it again and again. Okay, this is true in any Ramsey type question, right? You find a structure, it's usually tiny, you remove it and you keep going, right?
Okay, but the tech proof itself doesn't.
You don't
actually,
yeah.
That's kind of it's surprising that somehow it's a soft technique, but it actually is proving existence of one object.
Yes.
Right?
No, but actually, what it shows is something different. That the sunflowers are not sort of very special. So that even if I choose like a random coloring, you're gonna find like this monochromatic sunflowers. Or in this case, so actually, what this would prove if you combine this with the structural part that we removed that I had before. So if you put them together, you show that if I randomly color my elements red, green, and blue, and if I change this 1/3, let's say to 1/6 or something, so I change to some other, then with high probability, 50%, you're going to find a sunflower where the kernel, of course, they can control its coloring, but the petals are going to be 1 red, 1 green, and 1 blue.
Okay.
Yes. Okay.
Yes.
Yeah. Yeah. Okay.
Shachar, I have a question regarding this link definition. So I guess this is familiar from other contexts. One way to think of the link is that if you view, the set system as a polynomial, right? That every set corresponds to a monomial, then the link is just the derivative, right? You take
yes.
Take the derivative with respect to set.
Yes.
So is this useful? Like this view? polynomial?
I mean, I think it might be useful in some settings, not for this specific proof we have, because the proof we have is not algebraic at all. But yeah, these things are useful in other settings. But I don't see why it would be useful here.
Yeah, I'm also not seeing it, but I don't know. I thought maybe you could, it's the same thing that you connect it to DNFs. Maybe you can connect it to polynomials.
Yes. Maybe, yeah, I don't know. But then with polynomials, you add them up, right? So you sum them and you ask them about the sum. And here somehow it's crucial about the O and not the sum.
Right.
So it would exist in something, not something happening for many things. So this was actually important here. By the way, links, if people are aware, they come up a lot when you study high-dimensional complexes or hypergraphs, high-dimensional expanders, which is a very recent and trendy topic. So they come up a lot there also, understanding link structure and how this affects, hypergraph structure. So it's not I mean, we did not invent this term. It's a very common term in hypergraph.
Yes. There's another question in the.
Oh, the question Q&A. Oh, thank you. So, what does algebraic proof mean exactly? Okay. So, when I say algebraic proof, I mean usually it means you define some polynomial, and you say something. Oh, this polynomial has certain root structure or whatever, so it must be something. I don't know. I don't have a very precise answer, but like as examples, for example, this proof the cap set conjecture is algebraic. I don't know, of the proofs of the joints conjecture, that it was algebraic. Usually using polynomials somehow. The proof is using the fact that polynomials have some sort of, the roots cannot be arbitrary. Usually this is what I mean by algebraic, using something about polynomials or matrices or something linear algebraic. Okay, so maybe I'll continue. So here's the main technical results that we prove in this work, which is this spread set systems are satisfying. And here are the technical details. So I'm first recalling the definition. So we have a W set system. So all the sets have size W, or at most W. It is K spread, meaning that the links decrease exponentially fast with this base K. And again, PQ satisfying means that if we choose W from this P bias distribution, then there must be with high probability the set contained in W, in the elements we chose. So even if you choose each element, only a third of the elements, with high probability going to contain, your set is going to contain the sets there. And what we prove is for K something like log W, if you're K spread, then you are like 1/3, 1/3, so this is fine. But if you want to change 1/3, 1/3 to like say 1/10, 1/10, you just change some constants here that anyway they're not specified. So just constants. And we actually even understand the right dependence on P and Q. I'm not going to talk about this here, but in this sort of later works of Frankston and the one that Anoop also gave, they actually get a tight dependence on P and Q up to constants. So we understand everything there completely. And I'm going to give actually some examples toward the end of the talk showing why this type of approach will not get better than log W. So it turns out for this type of result, log W is the right answer and not constant. And we have some examples for that you'll see later on. So this is what I want to prove to you. So just to recap where we are so far. So we're assuming the set system has size, let's say K to the W, even more than K to the W, for K being something like log W. There is a structure case and a pseudo-random case. The structure case says the set system has a large link. In this case, there is a set T where the link is more than F over K to the T. So we just use induction for FT. And you see, this is what I think Paul was asking before. K is increasing in W, so I say increase to a link, the K is even smaller. So I, in particular, satisfy this condition. We use induction. The other case is this pseudo-random case where all the links are small. So this we call this K spread condition. This is just a complement of that. Where all the links are small, the decay exponentially fast with space K. We had this lemma that we need to prove, showing that this is 1/3, 1/3 is fine. We haven't proven that yet. That's a one missing ingredient. But we've seen a corollary of that showing that F must contain 3 disjoint sets, and hence here's a trivial sunflower. So that's the whole proof. And the only ingredient missing is this lemma here. That's what we're going to do in, I think, the second part of the talk. And actually, I think now might be a good time. I think we're looking for like a break, so now could be a good time for a break, and I'll continue in the second half.
Okay, so let's take a 10-minute break. I guess if you want to stick around in the break, you can, or otherwise you can, I don't know, have some coffee or take a short break, and let's see you again in 10 minutes.
So are we continuing the live streaming during the break or not? What's the rules?
We can pause it, I guess.
Live stream stays on, I think. You could pause the recording if you want to pause the recording.
Yeah, I paused.
Okay.
Yeah, I think it's better to pause it and then have the second half piece of. I thought you did it for the previous two talks, and I think it was very good. Well, the first half is not more high level, and the second half is maybe slightly more technical.
Right.
It's going to be the same thing here. Trying to follow the same approach.
Right.
Oh, by the way, I think that somehow somebody.
So, Avishai, these recordings, are they posted somewhere?
I see someone who wrote my name wrong. So, but I don't see how to fix this. I didn't set it up.
So it's in the Simon's website.
Oh yes.
I can post a link in the chat.
Yeah, we should fix Shahar's name.
Yeah, I don't have an option of renaming myself. I think somebody.
Where
is it?
I'll just change my name if it's easier.
Where do you see?
On top of the Zoom, the way the Zoom is set up on top.
Yeah. I mean, usually I have an option of changing the name, but now it doesn't let me change the name.
All right.
I can add the profile picture, but I cannot change the name. So anyway, if it's too hard, then it's fine.
I can change. Okay.
Okay. Good. Perfect.
Yeah. So okay, I'll post the link for the entire series, and then you can. Right, for individual talks, just press the links there. And I think already we have the talk of that you just finished. Like already Shachar's talk is there. So
really?
Yeah.
That's amazing. That's amazing. How did this happen?
I don't know. Shachar, when you said the proof for the colors, it sounded like this story, מעשה ב5 בלונים. So you need like five colors and then
5 colors. That's right. Yes.
So it's something about 5 colored balloons, and then like each boy or girl gets one of them, and like all of them.
The only question is why do you?
Right. Should we resume?
Yes, perfect. So everything is set up?
Yep.
I hope.
Yeah. Okay. Perfect. Okay, so let's continue. So welcome back, everybody. So let me remind you where we stand. So our goal is basically to put this one missing piece, which is this lemma here. Yeah, okay. So here's what we want to prove. We want to prove that the spread set system, which will remind you is this sort of type of pseudo-random set system, are satisfying, meaning that a random sparse set contains a set in my set system with high probability. And because we have this equivalence between set systems and DNFs, an equivalent way of thinking about it is to prove that the pseudo-random DNF is satisfied with high probability. And we know that, I mean, if people come from the TCS background, probably you know that we know from the classical works of Hastad and others, Asborov and Paul Beam, that random restrictions simplify DNFs. And what we're going to show that if you sort of say that my DNF is not arbitrary, so it's pseudo-random in a certain way, then you can do sort of mild random restrictions. So again, if you're coming from the TCS background, maybe you've heard about these topics. If you haven't, then maybe they're all new, but I'm going to explain everything. So now random restrictions and DNFs. And by the way, if you heard my CCC talk last week, that's going to be basically part of the talk on CCC. So you might have heard about this already. But then at the end, I have some new stuff. So you might want to hang around for that. So now I'm going to just be thinking about DNFs and present everything with respect to DNFs. And then at the very end, I'll tell you how this connects back to set systems. But I think it's more natural. I mean, at least for me, it's more natural to present this in the language of DNFs. So we have a Boolean function f. So it's a function of n bits to 1 bit. And what we're going to study are restrictions. And the restriction is where we take some inputs in 0, 1, and we fix them, some inputs, and we fix them to 0, 1, some input value. And the rest we keep free. So this is what I'm doing by star. So a restriction is row in 0, 1 star to the end, where the stars are all the alive variables, the one I haven't fixed so far, and 0, 1s are the one we fix to inputs. And in particular, we're going to study random restrictions where we do it randomly. So we randomly choose some p fraction of the inputs, and we're going to fix them to random values, 0, 1. And there are two ways you can do random restrictions. One is you say, well, I fix, let's say p is 1%. I want to choose exactly 1% of my input and fix them to 0, 1, and the rest I keep free. That's one variant. The other variant is that where I just do it independently for each coordinate. And these two variants are more or less basically the same. I mean, you can move from one to the other, so it doesn't really matter which one we're using. And the goal for us to show that with high probability, somehow the function simplifies. But not just, this is in general for random restrictions. So if you have a function and you fix some inputs to 0 and 1, you're hoping that the function now becomes simpler. And here's like a classical, so if, no, just one more. Here's a classical result from complexity theory. It says the following thing. Remember, we have DNFs, and our DNFs come from, we actually have monotone DNFs coming from set systems, but there'll be not, but we can, it's equivalent, just think about the regular DNFs, not without this monotone restriction. It doesn't really matter. So you have a with W DNF, and I'm going to choose a p random restriction, p the fraction of variables I fix to 0, 1, with p being very, very close to 1. Something like 1 minus 1 over 10W. So not quite 1 will be fixing everything, but very close to 1. So I fix all but something like 1 over W fraction of inputs. And I'll denote the simplified function, or the simplified DNF, by f of rho. And the switching lemma, which was first proved by Hastad, and then there was a simplified proof by Razborov and by Beam, is that by setting this p very close to 1, this restriction becomes very, very simple. In particular, there's some complexity parameter called decision tree depth, and with high probability it is very small. But I'm just going to tell you about what's called the baby version of that says, with high probability, your restricted DNF becomes constant. So what we do here, we have a DNF of with W. We fixed almost all of the variables to constant 0, 1, and with high probability, my DNF is now constant. Like, even though I still have like 1 over W fraction of variables that are alive, we do not need to know them. Like, the other variables already fix the value of the DNF. And I want to show you the proof of this lemma, because the proof of it uses an encoding argument, and we're going to use a similar encoding argument for what we'll try to do when we're going to study pseudo-random DNFs. So I want to show you the proof. In fact, in the parameters I said, it can even get something slightly better, but just half at 90%. So the proof has we need two definitions. So let me denote by R of k all the restrictions were exactly k stars. They're exactly k stars. So I choose k variables, I set them, keep them alive. All the other inputs, I set them randomly to be 0, 1, 50, 50. So all these restrictions. And that bad k are all these restrictions where the DNF did not become constant. They're the bad restrictions. And what we want to show is that these bad restrictions are a small fraction of all the restrictions. Actually, sorry, 1 second. Iris? There is a leak in the pool is leaking. Sorry. Some emergency needs to be fixed. Anyways, let me continue. So the way we're going to do it is we're going to find an encoding. We're going to encode bad restrictions, bad k, into some set that's going to be smaller than all the restrictions. It's going to be an injective encoding, so this would show that bad k is a small fraction of all the restrictions. And what is this set? Well, it's going to be it's going to be two parts. The first part is all the restrictions, where I'm saying there are not k alive variables, but k minus 1. So one variable less. So I'm fixing one more variable. And another part, which is an index between 1 and w. So this is just a set 1 up to w. And why is this good for us? Because remember, the way we set k is the number of variables we keep alive was n over 10w. So 1 over 10w fraction of the elements. And if you do the calculation, because we set already almost all of the inputs to 0 and 1, setting one more input restricts the number of restrictions by a lot. It decreases them by a factor of 10w. So fixing one more variable really kills a lot of restrictions. So even if I say add another piece of information that has w options, we get that this number of bad restrictions is at most 10% of all the restrictions. So we get this probability. So the only question is, how do we define this encoding? That's where all the magic happens. So what we want to encode is a bad restriction as a pair, another bad restriction rho prime, another restriction rho prime, not necessarily bad, it's a restriction, but where we have only k minus 1 alive variables and an index between 1 and w. So here's my DNF, and I have the terms sorted in some arbitrary order. And we define a process. So the first process, we'll say, let's take f of rho for my DNF when I fix the restriction. Because it's bad, it means, well, my DNF is not constant. Some terms are not killed and they're not fixed to 1. Those are still alive. Let's take the first one. And let's take the first variable that is a star in it. There has to be at least 1. And define rho prime in the following way. Take rho and fix this variable xj to a value b, 0, 1, so that this term is not killed. Meaning, if this xj appears in ti positively, I'm going to set it to 1. If not xj appears here, I'm going to set this to 0. So ti is not killed. It either survives or becomes satisfied. So this is how I define rho prime. And then the index is just going to be the following thing. I take all the variables of ti, and a priori we sort them in some order, and tell you which one of them is xj. So it's some number between 1 and w that is the index. So it's the index in all the variables of ti of this specific variable xj I chose. So it's in the same range, and that's encoding. And all that we need to show is that this encoding is injective, and we're going to show it by showing this algorithmic that you can, given this output, we can reverse the process and compute the input. So given rho prime in the index, we can just compute rho. So let's just do that. So let's show it's conjective. So first of all, I'm claiming given rho prime, I can find ti. Why? I'm just going to ask, well, what's the first term that is either satisfied or not killed in f under rho prime? Well, ti was the first in f rho, and so this xj to the specific value keeps this not killed. So ti is going to be this first one also under rho prime. And now, so I found ti. Now, given ti, I know ti. I know the index of xj in the variable, so I can find xj. So now I know ti and xj, and now I can just recover rho prime because I just set, now here to get from rho to rho prime, I set xj to some value. To go back, I just set it back to star, and I'm done. So this is an invertible process, and because it's an invertible process, it's injective. So this finishes the proof, right? So the main thing that we did here is encode bad restrictions in some way that allow us to bound the number of bad restrictions. And now you can ask, so this is a lemma that we proved here, this baby version of the switching lemma, and you can ask, is this tight? Do you really need to choose p very, very close to 1? Do you really need to fix almost all of the variables? And that's a problem sometimes. Like in some applications, we really want to fix only half the elements or 1% of the elements, not almost all the elements. Do we need that? And the answer is yes. So here's an example. This example is called the tribes function. It's basically a read once DNF. So I have the DNF with 2 to the w terms, and they're all disjoint. So each term is an end of w variables. And you can actually do a calculation and see that to make it constant, you really need to fix almost all of the inputs. Otherwise, it does not become constant. So it shows that the switching lemma, or even the baby version of the switching lemma, are tight. So if you make no assumptions on your DNFs, you really need to fix almost all of the inputs. So you need to make some assumptions on your DNF to hope to do better. So now I want to say, well, we can analyze milder random restriction that fix only a small fraction of the inputs if we assume the DNF is pseudo-random. So here's my DNF, and I'm going to say that the DNF is k-spread, which is the same definition as before, if it satisfies the following condition. Every t variables, for every number t, every t variables appear together in at most m over k to the t terms. Okay, so I have m terms in total, and this corresponds to the m sets I have before. This is the same as this condition that the links shrink, right? So I take t variables, I take the link defined by these t variables, all these terms contain these t variables, and then there should be a small fraction of them. They should decrease by a factor of k to the t. And that's the same as the underlying set system being k-spread. You know, for monotone DNFs, we just have this natural correspondence between variables and elements. If it's a non-monotone DNF, you get the same thing, but you need an element for xi and not xi. So you have you have both of them, but it's the same thing. So it's the same condition as before, but now we just view it from a DNF perspective and not from the set system perspective. It's exactly the same condition. So just to make sure we're all on the same page here, I have this very simple claim here. This is just to make sure that we all understand what's going on here, all the parameters. If a DNF has width W and is k-spread, then it proves that the number of terms has to be at least some number, at least k to the W. It cannot be very small. So why? Well, here's the answer. Take a single term. A single term contains W variables. But I know that if I have a single term, T is W, take W variables, the number of terms should be at most M over K to the W, but it's at least one. So M should be at least K to the W, right? So you should at least make sure that just to see that the parameters align. Okay, so going back to this tribes example, it is not very spread. It's only 2 spread. So in that sense, the tribes example is not pseudo-random enough. So what we're going to prove is that the following theorem: if a DNF is k-spread, where k is relatively big, something like log W, then p random restrictions are going to make it constant with high probability. So for example, if I want p to be a third, which is what we need for this 3 sunflower result, then we need k to be something like 3 log W. Right? But again, if you think of p as a constant, it should be something like log W. So for example, if I go back to this tribes example we had before, and I want to make this k-spread, I need to replace this top fan-in not to be 2 to the W terms, but k to the W terms. And then mild restrictions are going to work. So if you want one picture in your mind for what is an example of a more pseudo-random DNF, is just think about tribes where the top fan-in is not 2 to the W, but k to the W. Okay? But of course, what we have is a more general condition. We don't assume these terms are disjoint. We just assume that the links decrease fast. But this is what we want to prove. That's the same as the lemma we had before. And again, in particular, we can take p very, very close to 0 here. So we can take restriction that fix only a small fraction of the inputs, and by assuming the DNF is pseudo-random enough, we can still analyze, the probability that this DNF becomes constant.
Shachar?
Yes.
So you call this pseudo-random property, this k-spread. Do you have like a natural distribution for which the random behavior is k-spread?
Yeah, that's a very good question. I mean, I'm not sure that's precisely as it is, but this sort of morally corresponds to choosing sets randomly with the universe size somehow. Maybe you need the universe size to be k to the W, and you choose random sets. I think that would give you that.
So maybe the fact that you are choosing like a lot of sets compared to their size, right? So it's sort of like more than W.
Yes, exactly, yes. But also they don't somehow concentrate on a few elements, right? I mean, you could have k to the W, all of them containing the same W with 2 elements, right? So this won't help you.
But I thought that you also had like an example where the universe size is kind of small. And it's also...
Yeah, I'll get to that at the end. I'll show that later on. Yeah, we have an example where we have this condition where the universe size is small, but I'll get to that like in 20 minutes. So if you already seen this, then you know what this is going to, but otherwise, I'll get to that in a bit. Okay, so this is what we want to prove. That we have, again, think of P as some constant, like a 1/3 or something. So if F is K spread, and you're like something in log W, then with high probability DNF is constant, is going to be satisfied. Sorry, high probability will be constant. And the main idea will be that if you fix even a smaller number of inputs, something like P over log W, then this would reduce the width of the DNF from W to W over 2. And actually, this will be for most terms or for some average width, but ignore these are technical issues. So conceptually, what we want to say, we want to fix some small number of inputs and reduce the width of the DNF by a factor of 2. And turns out what you need to fix is P over log W. And this log W here is why it's log W here, because what we want to do now is, well, we want to repeat this log W times. If you repeat this log W times, the width becomes 0 and the DNF becomes constant. So we want to repeat this log W times, which means we'll choose this to be P over log W, and this is the main reason why we need to pay this log W. This is just the inverse of that, right? That's true. This should be the inverse of that. But to get to constant, you really need this log W here, or this log W in the denominator. Okay. So now let's do that. Again, that's a width reduction step. So we have a restriction, and we have a term. Some term that after this restriction stays alive, so it's consistent with rho. And typically, because rho only fixes like a small fraction of the elements, we expect a typical term. Most of the variables in it will still be alive. A few might be set to 0, 1 by this restriction, but most are going to be alive. Now, here's a crucial definition. This term is compressible if there is a term Tj that satisfies two properties. First of all, given this restriction and given Ti, the Ti is true, Tj is also true. So Ti plus rho imply Tj. So Tj might have some variables inside Ti and some other variables inside the restriction. It's consistent with both. So that's been consistent, but more crucially, I want Tj to have small width. So Tj should have less than half of W over 2, alive variables, stars, under the restriction. So Tj should be mostly have variables in the restriction and have at most half the variables in the stars. Okay, so this is what I mean where Ti is compressible. So why is this useful? Because if I have a compressible term, I could just replace Ti with Tj. Tj is some other term in my DNF. So I could say, well, under the restriction rho, instead of asking for Ti to be satisfied, let's just ask for Tj to be satisfied. And this doesn't lose anything, but now the width of this specific term went down to W over 2. Okay. So under rho, we can replace Ti with Tj. And the main claim that we're going to show that most terms in a DNF are compressible. And in fact, you can even analyze the average width, show that on average, the width decreases by a factor of 2. But let's ignore this average width condition. So we want to prove that. And again, the proof is going to be an encoding argument. So what we want to do is we want to encode. So before what we encoded our bed restrictions, now we're going to encode a restriction and a bed term. So a restriction here and a term that is bed in the sense that it is consistent with rho, but it is not compressible. So there is no Tj. Tj doesn't exist.
Shachar, can you go back a slide?
Yes, sure.
Yeah, I think this is like maybe the most new definition that may be worth pausing. But I have one question about it.
Yes.
So you're saying we can replace Ti with Tj. This is because we are thinking of like, right? We're thinking of both of them together, right? So
yeah, we're trying to satisfy either Ti or Tj, right? We're saying Ti or Tj, or a bunch of other things.
So if Tj is satisfied, then Ti would be satisfied, so we can just replace it. No. But like if
the other way around, if Ti is satisfied, then Tj is satisfied. So Ti or Tj is satisfied. So I can just remove Ti, right? Because if I satisfy Ti, then at some point along the way, I had to satisfy TJ as well.
Mm-hmm. Okay.
So Ti is redundant.
So that you can sort of merge these two terms to one of them.
Yes. And exactly. Under this restriction, we can merge Ti and Tj together to a single term, Tj. Very good. Yeah, so like Avishai said, this is maybe the one new definition here. So if there are any questions on this compressible definition, maybe now is a good time to ask.
So one comment. I mean, you had earlier said, well, typically Ti would have only a p fraction of things set by row. Tj is not typical in that sense here. It's got half of it set by row.
Yes, Tj is not typical, but we have so many terms, much more than exponential in W, so that we expect some terms to be atypical. So really, we're trying to exploit the fact that we have some atypical terms here. And the DNF, to satisfy DNF, it's not to satisfy one term. So you can just restrict attention to the atypical terms.
There's a question in the Q&A.
Oh, perfect. Thank you. What does Ti plus rho mean? Okay. So Ti plus rho, I just mean if I assume that the Ti is true and I assume that rho is true, so I assume both of them are true. So I set all the variables to make Ti consistent and rho, that's given, and I'm asking, does this imply Tj? So for example, if a variable in Ti is, let's say if x1 is in Ti, I'm going to set x1 to 1. If I have not x1 in Ti, I'm going to set x1 to 0. So I'm going to set the variables in Ti so that Ti becomes satisfied. And because Ti and rho are consistent, there's no inconsistency here, right? So setting all of rho the way rho is given to me, and setting Ti, so the variables of Ti, so it's satisfied, these two things are consistent. So I'm setting at most W new variables to values so that I satisfy both Ti and I'm consistent and I have a rho there. So did this answer the question? Let's see. There are more questions. Chat. If you have multiple Ti, then the Tj for each Ti might be jointly satisfiable with other original Ti being jointly satisfiable. Yes, it could be that multiple Ti have the same Tj. There's nothing against that. But remember, in a DNF, I don't care if I satisfy one term or 10,000 terms. Want to satisfy one term, I'm done. So to that extent, we don't care if we satisfy one or more than one term. That's a crucial aspect of a DNF. Like for example, a polynomial would count things. Here we're not counting. We're just saying either at least one or none. Yeah, so there might be many TIs with the same TJ, and that's fine. More questions? So I'll continue. Okay, so now I want to encode again a restriction in the term Ti that is consistent with this restriction, but is not compressible in some way that's show that these numbers are small. So first I'll take rho prime to be rho plus Ti. So again, this is the same as we had before. So we take the restriction rho, and then we set all the variables in Ti that were not fixed by the restriction so that they are all satisfied. This is rho prime. So I fixed at most W new elements. Now let Tj be the first term that is satisfied by rho prime. Now, Tj might be, there is such term because Ti is one such term, but there might be other ones. I don't care, take the first one. That's Tj. Now let's define V to be all the common variables of Ti and Tj. Okay. So it might be none, there might be some. So I take all these common variables and I define index 1 to be the following thing. I take all the variables of Tj. So I know Tj. V is some subset of this variable. So I index it. So since there are 2 to the W sets, possible subsets, this is one of 2 to the W subsets of the vowels of Tj. So I index it. I write the index of it. Now that I know these common variables, I set Fv to be all the terms in my DNF that contain V, where these variables appear in this term. And here's where we're going to use the fact that this is, if V is a big set, then this DNF has much fewer terms compared to the original DNF because the links shrink fast. So index now, in particular, TI, to trying to compress, is one of these terms because it has the variables v, the variables TI here. So it's one of these terms. And then F, so it's one of these terms. I just write the index. So in FV, I arbitrarily order them, and I tell you which index it is. The first one, the second one, the 100th one, and so on. That's going to be the second index. And lastly, we need one more piece to complete this picture, which is the restriction row on TI. Okay, we'll need that also. And I just write them all. This is my encoding. So my encoding are all the red parts here. It's this new restriction, row prime, these two indices, and this information S, which is the what happened this restriction row under TI. Which parts was stars or not. Okay. Now, first of all, let me show you why, given these 4 pieces of information, we can recover row and TI. And then we'll do calculation, why this actually compresses the size. So I claim that to recover here, there's nothing deep going on. Just go through this process one by one and just recover everything. Let's see. So I can recover row prime. I can recover TJ. Why? Because I know row prime, it's given to me. TJ, the first term, satisfied by row prime. I know TJ. Now, given TJ, I know the variables of TJ. I know the index of V here. This is index 1, so I can recover V. If I know V, I know FV. I know the index of TI and FV, so I know TI. And finally, if I know row prime and I know TI, so I know the new, and I know what was row on TI, I know which variables I added to row prime. And I can just set them back to stars and get back row. So this recovery here, they're just going through the steps. There's nothing deep going on here. So the interesting part is coming and trying to understand why does this actually compress information. So let's do a calculation. So here on the bottom, I just wrote the encoding argument. And now let's go through the steps. So there are 2 main observations. First of all, this may be the main one. The fact that TI is not compressible means that TI and TJ must have many variables in common. Why? If TJ and TI had very few variables in common, then TJ would have been mostly in the restriction part, so the number of stars in it would be very small. So because TI is not compressible, it said that any TJ that is consistent with TI and the restriction must have most of its variables in the stars. So in particular, the first one has this property. So V is more than W over 2, because this is the way we define compressible, W over 2. Now the second part is that because we're assuming, this should be spreadness, sorry. Because we're assuming the F is K spread, then we know that this link FV, this set FV, all the terms that contain V, there are much fewer terms compared to the full terms. We shrink by a factor of K to the size of V. And since the size of V is W over 2, it shrinks by at most K to W over 2. So we're going to use these two observations. So why? Let's do calculation. First of all, how many objects are we trying to compress overall? Well, the number of restrictions is RPN, and I'm here defining RPN to be all the restrictions where I fix PN variables. Okay, so RPN for this proof is all the restrictions where I fix PN variables. This is the number of rows I have in total. How many terms do I have in total? N. Okay, so this is the number of pairs overall, not just the bad ones, all of them. How many bad ones do I have? Well, for this, I'm just going to count the number of restrictions. So what is row prime? Row prime is a restriction like row where I fix W more variables. So it's some restriction in RPN plus K, where K goes from 1 to W. So I fix W more variables. And you can do a calculation and see this is at most RPN, but now it's more than RPN. So this is a larger number. I divide by P to the W. P is very small. So this is a larger number, right? So this is unlike in the Hastad switching lemma. In Hastad switching lemma, because we fixed almost all of the variables, fixing a few more variables decreases the number of restrictions. Here it's the opposite. Because in our restriction we fixed a small number of variables, we increase the number of restrictions, so we lose. So here we lose something. But we're going to recover that in the spreadness part. Well, the number of the first index is just 2 to the W sets. That's something. The number of the second index is where we gain. Because then, well, how many terms do I have consistent with V? At most FV, at most this number. So at most m number of terms, but now we gain much fewer terms. This term is going to compete with this term. And then this last part is this restriction also at most to the w. These two are just some other terms we need to add here. Not very interesting. So what we need to get this to work is we need the product of all these terms to be much less than this. This will show that most pairs rho and ti are good. For most restrictions, most terms can be compressed. So if you do the calculations here, you will see that the way I set up the parameters, I need k to be something like 1 over p squared. Okay, so you need k. And if you remember, we set p to be something like 1 over log w. So k will need to be something like log w squared here. So this will give us the bound that I promised you. If you optimize the parameters here, then you can get very, very close to 1 over p, but not quite. So we lose some lower order terms, but then there was this sort of follow-up works that were able to improve these terms. So again, this is what I promised you. This is the theorem I promised to you, that if k is something like log w over p, then, and in your DNF is k spread, then p random restriction is going to make it constant high probability. And now what is this approximate here? Well, the original proof we had lost some log terms here, but then this sort of follow-up work by Frankston et al. Actually were able to get this to be only a constant, so log w over p. And this is what, and the reason they needed to remove these log terms, because this is a phrase they actually need to prove this fractional expectation conjecture of Talagram. Again, and this and what Anup, Rao, and Tereta proved is this result. This result they reproved using information theory. So what Anup did is analyze the same encoding procedure, but using entropy instead of using counting. And what Terry did is analyze a different encoding procedure, sort of, but implicitly, where basically here, instead of choosing tj to be the first term satisfied by rho prime, somehow it's choosing to be a random term satisfied by rho prime. But and then he somehow simplifies the analysis using entropy. And you can read both of them. They're both. I mean, Anup has a paper on this, and Terry has this in his blog. Okay, now let me prove to you that this theorem, as stated, is tight. You cannot hope to do better. In particular, if you're hoping to use spreadness, you will never get beyond log w terms, even if p is like a third constant. And here's the example. So what's the example? So now I have small number of elements, w times k, and I arrange them in a grid. I have w rows and k columns. And here's my DNF. So every cell here is a variable, it could be true or false. My DNF is a monotone DNF. It says the following thing. In every row, there should be at least one. At least one. Okay? So if I want to write this as a DNF, so I'm going to have a term for every way of choosing an element in a row. So I have k to the power w terms. It has width w, because every term is just a single element in every row. You can check it is k regular, well, k spread. So regular is a term we had in a different incarnation of this paper. So when you see regular, just think spread. I need to fix this. K spread. But you can do a calculation and see that if I choose k to be something like log w over p, then p random restrictions do not make it constant. So this is tight. So I'm not going to do the calculation here, but it's a simple calculation to make. Okay. So this shows that if you're hoping to beat log w, you need to find a different approach. This theorem as is tight. So just to summarize, if we just think about DNFs, and for general DNFs, random restrictions need to fix almost all of the variables to simplify the DNF. But if my DNF is pseudo-random, so it's spread, then it's enough to fix a small fraction of the variables. And if we go back to set systems, so if you remember, set systems correspond to monotone DNFs when there are no negated variables. Well, it turns out if you study monotone DNFs, it's enough to consider restrictions that are not 0, 1 star, but just 1 star. You just fix variables to ones. And then if you just go through the definitions, the proof is the same. Then just a DNF becoming constant is the same as DNF becoming 1, because it cannot become 0. And then the set system is satisfied. So they're just following the definitions. I'm not going to do this here, but just sort of make sure the definitions match. So the proof I showed you is this more general proof for DNFs. if you just care about set systems and you just care about monotone DNFs, it's enough to study these monotone restrictions where you never set variables to 0, but then the same, everything is the same. Good. So maybe now is a good time for questions. Well, here's just summarizing the results we've seen. So we're studying W set systems. We want a sunflower size R, and I wrote here the bounds for the sunflower lemma, the conjecture, and what we proved, or the improved bound in the follow-up works, and which is also the limitation of the current technique. So I have several open problems I want to present here, but maybe before that, let's see if people have any questions about the proof so far.
Shachar, can you go back to the example?
Yes, definitely.
So correct me if I'm wrong. Like if I'm looking at this example where k is roughly log w, is it similar to like a tribe when I'm like doing like an OR of ends instead of an end of ORs?
Yeah, I mean, if you want to write this as a CNF, then it's an end of ORs, right?
Right.
I want to write this as a DNF.
Right. It's a very simple CNF. It's like it's the same as tribes, but as a CNF form.
Yeah. Yes.
Width log w.
Yes.
And then when you convert it to a DNF, it becomes a width w DNF with many terms.
Yes.
So maybe this also explain why this doesn't work, because we know that for the tribe function, it's right. It's somewhat like random restrictions do not work with these mild parameters.
Yes. So I see there's one question here asking about, can I briefly hint on how this helps with proving threshold results in random graph theory? Yes, I have a slide on that in a few minutes. So I'll get to that.
This example, it gives you a function which is k-spread, but doesn't give a counterexample because it has disjoint sets.
Yes, it has disjoint sets. Like for example, you take all the elements in the first column, the second column, and the third column. So it does have disjoint sets, yes. But if I color the elements randomly, it will not have this monochromatic.
So maybe you need a more algorithmic way to find the disjoint sets, some search. Clever search to find.
Yes. So I mean, we have various ideas on how to maybe try to modify it, but so far none of them work. So otherwise I would tell you about them. But yeah, I mean, you could try to say maybe we do random coloring, but we do something else. So you don't do it randomly, you do it somehow greedily, or you do All I know is random coloring and hoping for it to work doesn't work. But maybe something else does work. By the way, here if you say just take a random coloring and try to find like this monochromatic sunflower, this would actually exist, but what you will not find here are 3D random, like if you have random coloring here, then I will not find 3 disjoint sets, one being red, one being green, one being blue, because for example, with high probability, there is a row that's all red. So you cannot find the set that's all green. That's maybe one. If you don't care about the dependence on P, that's one way to say it. Okay. So let me continue. So now I'll tell you about a few applications. So one application is something that at least I found surprising, is this interesting structure result for intersecting set systems. So what is an intersecting set system? So I have a set system F on some universe N. We say it's intersecting if every pairs of sets in F intersect. That's an intersecting set system. And there is a very famous result in combinatorics called Erdos and Rado theorem that says, well, if I have an intersecting W set system, its size cannot be super big. So I mean, then how big could a W set system be in a universe of size N? Well, N choose W, right? All the sets of size W. But what they proved that, well, if it's intersecting, it has to be somewhat smaller. Its size at most N-1 choose W-1. And this is tight. Why? Because you can take all the sets that contain a special element. Let's take the first element in the universe. All my sets must contain this one element, and then on the other n-1 element, it could be arbitrary subset of size w-1. That's bounded tight. But I think this example is not very symmetric, right? There's this one element that is special. It belongs to all the sets. So here's a question. Could you hope to find a more symmetric looking intersecting set system where there is no one element or few elements that belong to all or to many of the sets? And one corollary of what we proved is that this is not true. So there must be a special set T where this number of sets in this set T is at most 1 over log n to the T. And this is just a direct corollary, because if this doesn't happen, then our set is K spread for K being log n, so it must contain many disjoint sets. In particular, it cannot be intersected. So just a way of reinterpreting the same result. But I want to make here a comparison to this case where it's not intersecting, but almost intersecting. So usually in combinatorics, when we have some extremal result, usually can relax some constraints and say, well, this should look roughly the same. And here is a case where this doesn't happen. So let me say the set system is almost intersecting, if not maybe all the pairs, but at least 99% of the pairs of sets intersect. And I'm claiming if this happens, then the behavior is very, very different. But if I take, for example, the family of all sets of n, of size something like root n, some constant, then if you choose this constant to be large enough, let's say 10, then it's almost intersecting. If you take 2 random sets of size root 10n, with very, very high probability they're going to intersect. But on the other hand, the links decrease much, much faster. You see the base here is log n, and the base here is something like root n. So there's a very, very big quantitative difference between intersecting set systems and almost intersecting set systems, which to me was surprising. I mean, the fact that make this constraint hard really changes qualitatively the behavior of the set system. You must now have some special sets. Okay, so this is one application. The other one was this question that arose on thresholds. So this is what Frankston and Khan, Narayanan, and Park proved. And let me give you one example. Let's say you're trying to prove something like that. You take GNP. So what is GNP? It's a random graph on n vertices where every edge appears at probability p. So there is this sort of classical result. Ask, well, what value of p do I need to guarantee that with high probability my graph has a matching? And the answer is up to constants log n over n. Now, what is a new proof? Given this conjecture, you say, well, take all matchings. How spread is a set of all matchings in a graph? And you can do a simple calculation. That's going to be something linear in n. So what you do is you take this number, you inverse it, it's c over n, you multiply by log n, you're done. So it's 1 over that times log n. And the point is that this is true now to always, for any type of structure trying to find. Usually this thing, I mean, you need this c log n over n. Usually it's easy to prove that p has to be at least that by some simple calculations. Otherwise, with high probability, the expected number of matching is going to be very small, and like less than 1. And then this new proof shows that by multiplying this by log n, anyway, that's this type of dependency. And getting this type of spread is just a simple calculation. So you can do it for matching or Hamiltonian cycles, or whatever structure might, or coloring, or whatever you're interested in, right? It's usually a simple calculation now. So this is what they proved. And turns out that to prove that, the main thing they needed is to remove these lower order terms in our analysis. And if you want to see more, then read our paper. Yeah. Any questions about that? I know that at least one person had a question on this application.
So this seems to show that this log n, another reason why this log n is needed, right?
Yes, exactly. That would be another reason why this log n is needed. Yes, that's true. Like, for example, if you think, what do I want? Let's say, think of a very simple event. I don't want any node to be isolated, right? So I want my graph to contain some connected graph. And saying, well, what's the probability of that? Well, every node, if I choose P to be 1 over n, then every node has a constant probability of being disconnected from everything, to not have an edge. And or let's say even something easier. I want every node to touch at least a single edge, right? Even a very simple event. I want every node to have at least degree 1. So if I choose P to be 1 over n, then with constant probability a node has degree at least 1. But to take a union bound over all n nodes, I need this log n, and log n over n. But so this is where you need to pay this log n, and this happens in many other similar scenarios for similar reasons. Somehow by some union bounding effect. And now we can ask, well, how far can we push this framework? Oh, there was a question in the chat. Let's see. Okay. Somebody saying hi. So again, if you want to use this spread condition as is, then this log W is tight. So I mean, whether you're trying to find satisfying conditions, or we have another example that I haven't showed you that shows that your set system could be K-spread, but it does not have 3 disjunctions. It even does not have 2 disjunctions. It's an intersecting set system. Sorry. Application 2 seems to have more to do with your lemma than with the sunflower as such. Yes, this is true. The application 2 is not with the sunflower lemma, but the way we prove the sunflower lemma. This is true. Yes, I mean, there's another example I haven't shown you, but we can actually build a set system that is intersecting, but K is very close to log W. It's log over log log. So to that extent, we can get much better than log, like maybe log over log log, but nothing better than that, even if you're just trying to find 2 disjoint sets. So in that sense, sort of, we're stuck at log W, although I think it's interesting to see whether it's actually log W or not. But there's one ray of hope here, which is there is a more refined notion of pseudo-randomness that might be useful. So let me call this K-bounded. So what's the difference? So in a K-bounded, we're saying the set system has K to Z, at least K to the W, and every link is small. So it seems to be the same. So what's the difference? In K-spread, the link size is relative to the size of the whole set system. If I make the set system bigger, I'm also allowing you to take the links to be bigger, as long as the ratio is maintained. But K-bounded, I don't allow you. You're allowed to take the set system to be bigger, but you're not allowed to make the links bigger. Okay, so it seems like a mild restriction. Now we have examples of K-bounded set systems which are not satisfying. So for that, we also need log W, but we don't have example of K-bounded with no 3 disjoint sets. So I want to, in the next slide, I'll tell you a bit more about that. But to me, that's one possibility that by refining the pseudo-randomness property, we might be able to get beyond this log W barrier and beyond what we can get with satisfying. So again, here on the top I have this definition. F is K-bounded if it has size at least K to the W, but every link is bounded in some absolute value, not relative to F. And here the conjecture. If F is K-bounded for some constant K, 100, then it cannot be an intersecting set system. Okay, another way of saying it, if I have an intersecting set system, it cannot be K-bounded for some large enough K. Just equivalent statement. And notice this will not directly imply anything about sunflower, but if not intersecting is the same as saying not containing 2 disjoint sets. So not intersecting means containing 2 disjoint sets. If I replace this with containing 3 disjoint sets, I would have a sunflower, or 3 or 4 or 5. And I don't think there should be any major difference. If you can prove this for intersecting set systems, this should be the same. I don't see any major difference. So I think a very interesting open question is to prove or disprove this conjecture. I mean, either to find an example of an intersecting set system that is K-bounded for K, which is super constant, or to prove it does not exist. And again, we have an example like that if we replace K-bounded with K spread. So in our example, it's K spread with K being like log W, but F is slightly more than K to the W. So somehow doesn't quite satisfy that. And I believe the example we have it in the paper. Okay, so a bit of what future work. So I mean, one thing I'm interested in trying to explore, I think it would be good if people try to do this as well. I think, well, we have these new techniques. What else can we apply them for? So there were these applications to random graph theory that you were very interesting to learn about. And you can ask, what about other remedy problems in combinatorics? And there are many where we don't know the right bounds, and we can hope that maybe, you know, these techniques will help us make progress. And there are also these questions coming from TCS about structure of DNFs. And if we go to my CCC talk they gave last week, I speak in some more detail about that. There are various questions that we are interested in about structure of DNFs that we don't understand, and maybe these techniques could be useful. And by the way, we already had one application of a similar type of ideas where we now have like optimal bounds on something called DNF compression. But there are other questions that are interested that we still don't know, like for example, that are more about Fourier structure of DNFs. Another area where this seems to be useful, but we only have some preliminary results so far, is in lifting theorems in communication complexity. That's where these techniques seem to be useful to get better bounds. And of course, we should still prove the sunflower conjecture. Okay, so that's it. Thanks.
Thank you, Shachar.
It's a good time for questions.
Right, I guess. Right, so let's take a few questions.
Chat. Oh, thanks, Rocco.
I guess we weren't shy and we asked questions along the top.
Very good. We should. But I know if people have some open-ended questions or anything. Really.
So I know some versions of sunflowers were used in circuit complexity. So do you think you can improve circuit complexity bounds using your methods?
It's a very good question. So I know that many of these techniques were used when some were used in circuit complexity, many applications were in a fixed parameter tractability. I think for some of the applications, this doesn't prove anything because their R was bigger than const, even bigger than W, in which case the R to the W term was a dominant one. In some applications, yeah, I mean, I know that Ben Rossman had some applications where they get like better low bound for monotone circuits. So that was one area where people use the sunflowers. I'm not sure.
So using the robust sunflowers, we're able to improve the monotone circuit lower bounds to exponential and square root n.
Yes.
So this is a paper in Latin 2020.
Yeah.
There's another question in the Q&A.
Yeah, but Ben is the expert on the thing, so he should answer. If there are any other applications in circuit complexity.
So Shachar, there's another question in the Q&A.
Oh, there's another question in the Q&A, okay. Why the exponential decrease condition on all t instead of t of bounded size related to W? So if you think about the proof, we needed t to be of size W over 2. So it's already pretty big sets to begin with. But really, if you want to optimize the parameters, then you need to choose t to be of size very big. So much closer to W. So in the proof we had, it was like 1 minus epsilon times W, where epsilon was some slowly decreasing function, and of these newer proofs, they don't do it explicitly, but implicitly these things happen there. So I think we do need this condition for t's of size almost up to W. So why not ask all the way up to W? It doesn't really save you much. In particular, I think we can build examples that are spread up to some size, but do not satisfy the satisfying condition. So you do need. So we have some examples where you do need that, at least up to size linear in W, let's say.
All right. So I want to thank Shachar again. This was excellent. I really enjoyed it. And our next meeting is on Wednesday in 2 days. We'll have, I believe, Renan and Zhang, and we will send our reminder via email. All right.
And also let me thank Avishai and Prasad for organizing this series. I think it was really great. I mean, I watched the previous 2 talks and it was really nice talks and really nice. Thank you for organizing it.
Thank you for talking.
Thank you for a really nice talk today.
Thanks.
See you.
Bye-bye.